100 feet of rope. So I hope I have plenty of rope when I get down there.
So I've been down here before, but I remember this is kind of a cool section where you got a Hercules dynamite box with the dynamite still in it, and a little shelf, some California Capco. These are the blasting caps. So there's actually a blasting cap itself there, which is kind of dangerous. And this little shelf they built. Let's see what this is. No brand on that one, but pretty cool stuff. One day I'll come in here and dig all this out. You can see some pack rats have been down here. We need to get down deeper, and that is what we will do. You can see up here what a terrifying void this is. There's just so much that they took out of here. See the timbers, they're trying to keep it apart. And we are headed down.
Back then, they didn't have the modern reinforcement technologies that we have today. So they tried to take out everything valuable that they could and leave behind just enough so the whole thing didn't collapse on them. And it was also called stoping, and there were a few strategies they used that I could see while I was going down. The first was called room and pillar mining, where the miners would leave pillars and ledges in these giant openings for natural support. And to get from ledge to ledge, the miners created crude wooden ladders.
Some pants. A button. I don't know what these are. I can't believe I didn't see them last time I was down here. It's like canvas. Oh, suspenders? There's some suspenders. Oh, and then a cinch in the back. That's worth taking up. I'll take that up.
I'm on a little platform now, and you can tell by the light over there that this actually still has some access to the outside, because there's a lot of dead animals down here that have been falling. But it's below this that I make the juncture between the more dangerous pit and the easier way I took last time. I'm hoping, just a minute we'll get onto that ledge. We'll make the decision to go towards the area I want to, and see if we can't get to where we need to go. But
Never ceases to amaze me that all of this was taken out by humans, 150 years ago. It's so crazy. You can see here how they're using this kind of duck canvas to prevent dirt from sliding on the cracks of this platform they built. And sometimes, instead of using this canvas, they'll use old jeans or denim or scraps or whatever they have. Who knows, underneath this there might be some, but creepy how they're just building all these little platforms everywhere.
Eventually, after squeezing myself through more holes than I'd like to, I got to the juncture again.
All right, this is it. The pit of death side that I didn't want to go down. We're gonna go down. Come on.
It must bring together the strangest elements of quantum mechanics and relativity, the rules on the macro scale and the micro, which is really hard to do because there are some very weird things going on in the quantum world. Uncertainty, quanta, superpositions. So, let's begin there. After my last video on this topic, I got loads of different comments from you all, eager to hear my take on the answer to everything. I claimed last time that I believe some form of string theory offered the best chance at a unified theory of everything. It's time to show you how much heavy lifting strings can do on the quantum scale. I'm Alex McColgan and you're watching Astrum. While I don't claim to have solved the theory's mathematics, I believe that I've come up with a model that pieces all the phenomena together. Quantum physics' mathematics has rapidly overtaken its understanding of why the things we observe are going on. Let's try to help conceptual understanding catch up. As I said in my last video, it all starts with strings. Let's discuss a few properties of a vibrating string. This will help us to see why they lend themselves to quantum principles. We need to start with that first word, quantum. Simply put, quantum is derived from the same root as the word quantity. It's the strange principle that, on a small enough scale, the universe seems to work in discrete quantities rather than operating on one continuous scale. This is a little unintuitive, much like many things in quantum mechanics. So let's illustrate what we mean with an example. If you are running, I could ask you to half the speed you're running at. You could half your speed again and again and again. Is there a limit to how many times you can half that speed? While you might struggle with the precision necessary to do it, in classical physics, there's no reason you couldn't keep halving and halving your speed indefinitely, as there's no limit to the number of times you can divide a number by 2. There's always a smaller number. In the quantum world, this is not so. When it comes to energy levels, momentum, and other attributes, when you reach a small enough number, you discover that the universe does not work on a continuous scale, but rather in discrete quantities. An electron in a hydrogen atom can have exactly minus 13.6 electron volts of energy, or it can have minus 3.4 electron volts, but under no circumstance can it have an energy level between those values. This has been proven experimentally. A theory of everything must make use of an underlying universe geometry that is fundamentally quantized. The concept of some kind of web of strings fits that bill well, particularly when you bring in the transverse standing waves and harmonics. When plucking a guitar string, a standing wave can form that has one peak or two, but not a value in between those. This is because harmonics are formed by a combination of waves traveling along the string in one direction, perfectly resonating with waves traveling in the other. If the speed or frequency of the waves don't line up perfectly, the two waves will ultimately disrupt each other, leading to the collapse of the standing wave. Only waves with just the right amount of speed and energy can create standing waves on a given string. So immediately, we have an interesting mirror to our observation that subatomic particles have quantized momenta and energy levels. So do standing waves on strings. The next interesting point to note about waves is that by combining the correct sequence of sine waves, you can create any wave pattern of wave you might desire. Handy for creating the rich complexity of a universe. This mathematical principle was first discovered by Jean-Baptiste Joseph Fourier, a French mathematician, and is very useful in the study of heat transfer and vibrations, as it works the other way too. Any wave can be broken down into a number of constituent sine waves. When two waves try to occupy the same place, they will amplify each other if they're both rising or both falling, but will cancel each other out if they're in opposition. This can lead to all sorts of waves being formed: square waves, intermittent waves, and even waves that only have a single peak and are flat at all other locations. This becomes easier to do the more waves you have to overlap. This is an interesting observation, as it helps answer an important question that any theory of everything must be able to answer. Where do particles come from? When I say particles, I'm not specifically talking about molecules or atoms, but the components that make these objects up. Atoms split into protons, neutrons, and electrons. Protons and neutrons split into quarks, and there are leptons and bosons. Without needing to go into exactly what all of these things are, or why they have some of the weird names that they do, I mean, who decided to call a quark strange, charm, or bottom? It's enough to say that they come in many different flavors. These are the smallest building blocks of reality that we know of so far. Why do they exist? Well, in a model using strings, they are the rising and falling of a wave. This matches Einstein's observation that mass and energy were essentially just the same thing in different forms, as laid out in his E=mc² equation. A wave is the motion of energy. Mass can be that too. The narrower the peak of the wave, the more defined a particle is in terms of its location on that string. You might take issue with the idea that both of these waves represent the location of a single particle. However, curiously, this matches another important facet of particles. They sometimes are a little vague about where exactly they are in space. If you know much about quantum mechanics, you have likely heard of Heisenberg's uncertainty principle. This is the idea that we cannot know a particle's momentum and position at the same time. We get a decent approximation at large scales. It's pretty easy to see where you are and where you're going, but at small enough levels, this becomes impossible to do. The more precisely we know where a photon is, the less information we have about its momentum, and vice versa. This isn't just because we have bad techniques for observing them. This is apparently a fundamental truth. If we think about particles being the sum of many overlapping waves, however, this suddenly makes a lot more sense. Take a look at this wave. It is perfectly defined in terms of where it is going, but if we consider the peaks of this wave to represent the location of the subatomic particle, or at least the possibility that the particle is at this location, there are a lot of places it can be. So, for this given string, we have perfect knowledge as to its speed and direction, but are uncertain about its position in a given space of string, perfectly in line with Heisenberg's uncertainty principle. If we converge several different waves into a single point, we can take advantage of Fourier's mathematical trick to cancel out some of the peaks of our wave. The more waves we add coming in from different directions, the more our particle becomes defined in space. But look at our particle now. How many strings are running through it? Each of these is a separate vector line, representing momentum in a different direction. it's no longer quite so possible to pin down where this particle is going next, as there are several options that could be true. Perfectly pinning down a particle in terms of its location would require vector lines that could lead anywhere. This is starting to get into territory where you would need information from the entire universe before a single particle can be truly solved in terms of its location in space and time, which is a little headache inducing. Perhaps the universe makes do with close approximations most of the time, until someone looks closely. For this model, we must discard our concept of a particle as a localized object, but instead we define them as the convergence of different waves, coming together at a single point and then diverging again. This divergence doesn't feel right to us. We are uncomfortable with the idea of our particles only being really there at a given moment and dissipating afterwards. However, those of you familiar with the double slit experiment, which I have covered in an earlier video, will recognize that this is an uncanny match to another odd experimental result. A single photon released from an emitter and passing through two slits will somehow pass through both slits, interfering with itself on its journey. The photon reaches the far detector as a single particle again, indicating a new convergence at that point, but by sending many photons along this path, it becomes clear that interference is taking place in the intervening space. The photon seems to leave as a particle and arrive as a particle, but in the intervening space, it takes on the properties of a propagating, rippling wave. Already we begin to see how some of the strangest aspects of the quantum world fit with the idea of strings carrying waves of energy. But this is only the first part of my model. To really see how much a theory matches the universe around us, we need to explore the motion of particles across time and space. To better understand entanglement and superpositions, and to do that, we need to explore how strings lead to gravity, time dilation, and other principles of relativity on larger scales. We need to have a clear concept of how time works. My model accommodates that, but it will have to wait until my third video in this series to fully explain. In the meantime,
Hello wonderful person, this is Anton, and today we're going to discuss the strangest comet in the solar system. And forget 3i Atlas, forget other interstellar comets, because we actually have something much weirder right here, and you're looking at this object in this image. This is known as 2060 Chiron, one of the most puzzling and most dynamic objects in the solar system, representing a small icy body that actually defies easy classification and behaves both like an asteroid, a comet, and potentially something else. But more importantly, in some of the most recent studies, scientists have also discovered that it's actually doing something we've never seen anywhere. It's now developing a new complex ring system right before our eyes. And so let's discuss these studies and these discoveries in more detail. But I guess first let's discuss exactly where this object is, what we think it is, and how it compares to some of the other stuff we know in the solar system. And technically, Chiron classifies as the first member of a very peculiar class of objects known as centaurs, named after mythological half-humans, half-horse creatures, because here centaurs are also basically these hybrid objects. They orbit the Sun mostly between Jupiter and Neptune, with their orbits usually crossing at least one of these larger planets. Here are roughly where some of these objects are located. And it's the location that makes these objects so fascinating. They're basically trapped in these very unstable orbits that are only going to survive for maybe a few thousand years. And that's because they're constantly being influenced by the gravity of the giant planets, with all these objects constantly being reshuffled and moved across the solar system. And though for some of them they're going to maintain these orbits for a few million years, the majority of them are not going to be that lucky. But when it comes to their origin, we actually think they come from much farther away, possibly the Kuiper Belt, basically the location where you find Pluto and a lot of similar objects. And so as the orbit of some of these objects interacts with Neptune, they might become perturbed and might become trapped in the inner solar system. So centaurs, in essence, are kind of like transitional stages between stable Kuiper Belt objects and much shorter period comets known as Jupiter family comets. and both of these types of objects have been discovered in a lot of different locations. And that of course makes centaurs very important for planetary science. Not only do they represent the remnants of the early solar system, usually containing a lot of primordial ices and a lot of primordial materials, but also by studying them, we can kind of look back in time, discovering how the solar system evolved just by seeing the emissions from these rocks and by seeing how they change. And the thing is, most of these objects are relatively new to us. As a matter of fact, the first object, Chiron, was only discovered in 1977. It was discovered by Charles Cole, and at the time it was initially recognized as the first member of this new population orbiting between the asteroid belt and the Kuiper belt. And though at first we thought it was just an asteroid, which is why it's called 2060 Chiron, or basically 2060th asteroid ever found, in 1989, or approximately 12 years later, astronomers noticed something super strange. It was also exhibiting cometary behavior. It became very bright by 1988, and at this point it was approximately 12.
She went camping, and what the camera caught will terrify you. The 11 February 15th, 2022, North Vancouver. Natasha, living solo in a Dodge Grand Caravan with her 3 cats, had just parked in a quiet lot to cool off after a stressful day of van issues.